close your eyes. Let the weight of the day fall away from your shoulders and allow your mind to travel somewhere impossibly far from here. Imagine, for a moment, that you are standing on the surface of a world. Beneath your feet, the ground is solid, real, made of rock and ice that formed billions of years ago in the same cosmic furnace that built the Earth. There is gravity here. There is atmosphere. There is a landscape stretching out before you in every direction. But when you look up, there is nothing. No sun, no warm golden disk climbing above the horizon. No pale blue sky fading into twilight. There is only darkness. A vast, endless, all-encompassing darkness broken only by the faint and ancient light of distant stars. Stars so far away they offer no warmth, no comfort, only a reminder of how profoundly alone this world truly is. You are standing on a rogue planet, and on this world the sun never rises. Not today, not tomorrow, not ever. Let that thought settle over you, like a blanket. There is no dawn coming. There is no season waiting to change. The concept of a year has no meaning here, because a year is measured by orbits around a star, and this planet orbits nothing. It drifts. Slowly, silently, imperceptibly, it moves through the interstellar void, the enormous dark spaces between the stars, carried along by the faintest gravitational whispers of the galaxy itself. It has been drifting like this for a very long time, perhaps for billions of years, perhaps since before the Earth even existed, and it will continue to drift long after every star you have ever seen in the night sky has burned out and gone cold. This is a story of rogue planets, sometimes called free-floating planets, sometimes called nomad planets, sometimes called orphan worlds. They are planets without parent stars, worlds without solar systems, celestial bodies that possess all the characteristics we associate with planets: mass, composition, sometimes even atmospheres and magnetic fields, and yet they belong to no stellar family. They wander the galaxy alone, unbound, untethered, sailing through the darkness on trajectories that may never bring them close to another star for millions or even billions of years. They are among the most mysterious and haunting objects in all of astronomy, and for a long time we did not even know they existed. The idea that planets might exist outside of solar systems is not new. Astronomers and philosophers have speculated about such objects for centuries. But for most of the history of planetary science, the assumption was simple and intuitive. Planets form around stars. They orbit stars. They are defined in part by their relationship to a star. When the International Astronomical Union famously debated the definition of a planet in 2006, a key criterion was that a planet must orbit the Sun, or, by extension, a star. Rogue planets challenge that definition at its foundation. They are planetary mass objects that orbit no star at all, and their existence forces us to reconsider what we even mean when we say the word planet. The first serious theoretical predictions of rogue planets came in the late 20th century, when the computer simulations of forming solar systems began to reveal something unexpected. As planets coalesced from the swirling disks of gas and dust around young stars, the gravitational interactions between them were far more violent and chaotic than anyone had imagined. Planets did not simply form in neat, well-spaced orbits and stay there. They pushed and pulled on each other, migrated inward and outward, and, in many cases, flung each other out of the solar system entirely. The simulations suggested that planet ejection was not a rare accident, but a routine part of solar system formation. For every planetary system that settled into a stable configuration, one or more planets may have been cast out into the void. The observational confirmation came gradually, and then all at once. In the early 2000s, astronomers began detecting objects in star-forming regions that had planetary masses but no apparent host star. These were initially called planemos, short for planetary mass objects, and their discovery sparked fierce debate. Were they truly ejected planets, or had they formed in isolation, collapsing directly from small clouds of gas the way stars do, just at much lower masses? The answer, as we now understand it, is both. Some rogue planets were born around stars and later expelled. Others were never bound to a star in the first place. They formed alone, in the cold, dark spaces between the stars, and they have been alone ever since. But it was a study published in 2011 that truly shook the astronomical community and brought rogue planets into the public consciousness. A team of researchers led by Takahiro Sumi of Osaka University in Japan, working with data from the Microlensing Observations in Astrophysics Collaboration, known as MOA, and the Optical Gravitational Lensing Experiment, known as OGLE, announced a remarkable finding. By monitoring millions of stars in the direction of the galactic center and watching for the telltale brightening caused by gravitational microlensing, the bending of light from a background star by an intervening massive object, they detected a population of planetary mass objects that appeared to have no host star. Their estimate was staggering. They suggested there could be roughly 2 Jupiter-mass rogue planets for every star in the Milky Way. 2 for every star. In a galaxy containing somewhere between 100 billion and 400 billion stars, that would mean hundreds of billions of rogue planets, perhaps as many as several hundred billion, wandering the galaxy in total darkness. Let that number wash over you. Several hundred billion. It is a number so large that it resists comprehension. If you tried to count to several hundred billion, one number per second, it would take you thousands of years. And each one of those numbers represents a world, a real, physical, three-dimensional world, with a surface and an interior and a history. Some of them are gas giants like Jupiter, massive spheres of hydrogen and helium with no solid surface, their swirling atmospheres slowly cooling in the absence of stellar radiation. Others are smaller, rocky worlds, perhaps not so different from Earth in their composition, with iron cores and silicate mantles and frozen surfaces locked in perpetual night. Every single one of them is out there right now, somewhere in the Milky Way, drifting through the dark. And we cannot see almost any of them. That 2011 estimate has been refined and debated in the years since. Some subsequent studies suggested the number might be somewhat lower, perhaps closer to 1 rogue planet for every 4 stars, which would still yield tens of billions. Other studies, using different methods and different assumptions, have pushed the number higher. A study published in 2023 by researchers analyzing data from the Nancy Grace Roman Space Telescope precursor surveys suggested that smaller Earth-mass rogue planets might be even more common than the gas giants, potentially outnumbering stars by a factor of 20 or more. The uncertainty is large, because detecting rogue planets is extraordinarily difficult. They emit no light of their own, or rather, they emit only the faintest infrared glow from their slowly cooling interiors, and they are incredibly small and dim compared to stars. Finding them is like searching for a single unlit candle in a dark forest that stretches across an entire continent. think about what this means for the galaxy we live in. We are accustomed to imagining the Milky Way as a vast collection of stars, hundreds of billions of luminous points scattered across a disk 100,000 light-years in diameter. We picture solar systems orbiting those stars, planets warmed by stellar light, moons circling those planets, asteroids and comets tracing their elliptical paths. But if the estimates are even approximately correct, then the most common type of planet in the galaxy is not one that orbits a star. It is one that orbits nothing. The galaxy is not primarily a collection of solar systems. It is a collection of wandering worlds, drifting through an ocean of darkness so vast that the stars themselves are merely islands, rare points of warmth and light separated by incomprehensible gulfs of cold, empty space. The rogue planets outnumber them all, and they are everywhere. Between the stars, between the spiral arms, in the halo of the galaxy, in the spaces between galaxies. Everywhere there is darkness, there may be worlds. There is something deeply moving about this idea, something that touches on loneliness and resilience and the sheer improbability of existence. Consider a rogue planet that was ejected from its solar system 4 billion years ago. For 4 billion years, this world has traveled alone. It has crossed distances so vast that light itself would need thousands of years to traverse them. It has passed through regions of space so empty that the nearest atom of hydrogen might be a meter away. It has experienced no seasons, no tides, no eclipses, no sunsets. It has known nothing but the slow, steady cooling of its own interior, the gradual loss of the primordial heat it carried with it from the moment of its birth. And yet it endures. It is still there, still a world, still a planet by any reasonable definition, still possessing mass and gravity and geological history. It simply has no sun to call its own. If you enjoy falling asleep to these journeys through the cosmos, consider subscribing to the Science Pillow. Every week, a new documentary arrives, designed to carry you gently through the wonders of the universe and into a peaceful sleep. Some of these worlds may have known warmth once. A rogue planet that was ejected from a solar system may have spent millions or even billions of years orbiting a star before it was cast out. It may have had seasons. It may have had liquid water on its surface. It may have had, however briefly, the conditions we associate with habitability. And then, through no fault of its own, through nothing more than the blind mechanics of gravity and orbital dynamics, it was torn away from all of that and sent tumbling into the void. The warmth faded. The oceans froze. The atmosphere, if it had one, may have partially collapsed. Some gases freezing out onto the surface as temperatures plunged toward the cosmic background temperature of just 2.7 Kelvin, barely above absolute zero. Everything that world once was, everything it might have become, was lost in the darkness. And yet, as we will explore in the sections to come, not all hope is lost for these wandering worlds. Some of them may carry their warmth with them, locked deep inside, in the form of radioactive decay and residual heat from their formation. Some of them may possess thick atmospheres of hydrogen that act as insulating blankets, trapping that internal heat and maintaining surface temperatures far warmer than the void around them. Some of them may even have subsurface oceans of liquid water, kept liquid not by the warmth of a star, but by the slow, patient heartbeat of their own geology. The idea that rogue planets could harbor liquid water, and perhaps even life, is one of the most extraordinary possibilities in all of modern astrobiology. But we are getting ahead of ourselves. For now, let us simply sit with the wonder of it. Billions upon billions of worlds drifting through the galaxy in silence. Worlds that have never seen a sunrise. Worlds that carry frozen oceans and dormant volcanoes and mountain ranges that no eye has ever observed. Worlds that are, in every meaningful sense, real places, as real as Mars or Venus or the Earth itself, and yet so far removed from the warmth and light of stars that they exist in a kind of cosmic solitude we can barely imagine. They are the dark matter of planetary science, not the exotic dark matter that physicists puzzle over, but dark in the most literal sense. They are planets that emit no light, reflect no light, and hide in the vast spaces between the stars, invisible to almost every instrument we possess. The question that naturally arises, the question that draws us deeper into this story, is how? How does a planet end up alone? What cosmic misfortune, what gravitational catastrophe, what accident of formation leads a world to wander the galaxy without a star? The answer, it turns out, is not simple. There is no single mechanism, no one explanation. Rogue planets are created through a variety of processes, some violent and sudden, others gentle and gradual, and each process tells us something profound about the way solar systems form, evolve, and sometimes fall apart. To understand the rogue planets, we must first understand the places they came from and the forces that set them free. And that is where our journey takes us next, into the turbulent, chaotic, breathtakingly beautiful process of solar system formation, and the gravitational dramas that can tear a young world away from its star and send it sailing into the endless night. Section 2. How a planet loses its star. To understand how a planet becomes a rogue, we must go back to the very beginning, to the moment when planets are born. And that moment, like so many moments in the history of the cosmos, begins with a cloud. Not a cloud of water vapor drifting across a blue sky, but a cloud of gas and dust drifting through the interstellar medium, the vast, tenuous material that fills the spaces between the stars. These clouds are called molecular clouds, and they are among the largest structures in the galaxy. A single molecular cloud can span dozens or even hundreds of light years, and contain enough material to form thousands of stars. They are composed primarily of molecular hydrogen with traces of helium, carbon monoxide, and tiny grains of dust, silicates and carbon compounds and ice, each grain smaller than a grain of sand, each one a potential building block for a future world. For millions of years, a molecular cloud can drift through the galaxy in a state of relative equilibrium, its own gravity pulling it inward while its internal pressure and turbulence push it outward. But equilibrium in the cosmos is always temporary. Sooner or later, something disturbs the cloud. Perhaps a shock wave from a nearby supernova ripples through it, compressing regions of gas to higher densities. Perhaps two clouds collide, or a cloud passes through one of the galaxy's spiral arms and is squeezed by the increased gravitational field. Perhaps the cloud simply reaches a point where a particular region becomes dense enough that gravity overwhelms pressure, a threshold known as the Jeans mass, named after the British physicist Sir James Jeans, who first described it in the early 20th century. Whatever the trigger, the result is the same. A region of the cloud begins to collapse. The collapse is slow at first, measured in hundreds of thousands of years, but it accelerates as the infalling material grows denser and gravity strengthens. The collapsing region fragments into smaller clumps, each one destined to become a star or a small group of stars. As each clump contracts, it begins to spin faster, the way an ice skater spins faster when she pulls her arms in, a consequence of the conservation of angular momentum. The spinning material cannot all fall directly onto the growing protostar at the center. Instead, it flattens into a disk, a vast rotating pancake of gas and dust that surrounds the young star like a cosmic dinner plate. This is the protoplanetary disk, and it is the birthplace of planets. Protoplanetary disks are stunning objects. They can extend hundreds of astronomical units from their central star, where one astronomical unit is the distance from the Earth to the Sun, roughly 93 million miles. They contain anywhere from a fraction of a percent to several percent of the star's mass, which translates to enormous quantities of material, enough to build dozens of planets and thousands of moons, and millions of asteroids and comets. The disk is not uniform. It is a complex, turbulent environment, with temperature gradients that range from thousands of degrees near the star to just a few tens of degrees in the outermost regions. Close to the star, where temperatures are high, only metals and rocky minerals can exist as solids. Farther out, beyond a boundary called the snow line or frost line, water can freeze into ice, and beyond that, other volatile compounds like methane and ammonia can freeze as well. This temperature structure has a profound influence on the types of planets that form at different distances from the star. Planet formation within these disks proceeds through a process that is, even after decades of study, not fully understood in all its details. The broad outline, however, is increasingly clear. It begins with the dust grains, those tiny particles of rock and ice that make up a small but crucial fraction of the disk's mass. These grains collide with one another as they orbit the star, and under the right conditions, they stick together. Grain by grain, the particles grow larger, from micrometer-sized motes to millimeter-sized pebbles to centimeter-sized stones. This process, called coagulation, is driven by gentle collisions in the turbulent gas of the disk, and it is the first step on the long road from dust to planet. As the growing bodies reach sizes of roughly a kilometer across, they enter a new regime. They are now large enough that their own gravity begins to play a role in attracting additional material. These kilometer-sized objects are called planetesimals, and their growth accelerates dramatically through a process called runaway accretion. The largest planetesimals, by virtue of their slightly greater gravity, attract material faster than their smaller neighbors, growing at an ever-increasing rate. In a relatively short time, astronomically speaking, perhaps a few 100,000 years, the largest planetesimals have swept up enough material to become planetary embryos, objects roughly the size of the Moon or Mars, with masses of perhaps a tenth of Earth's mass. These embryos are the seeds of future planets. What happens next is where the story becomes violent. The protoplanetary disk, which once contained countless planetesimals and embryos all orbiting in roughly the same plane and the same direction, begins to experience gravitational instabilities. The planetary embryos are large enough to perturb each other's orbits significantly. Their gravitational fields tug and pull, bending orbits from circles into ellipses, tilting them out of the plane of the disk, creating a swarm of increasingly eccentric and inclined trajectories that inevitably lead to close encounters and collisions. This period, sometimes called the giant impact phase, is a time of extraordinary violence. Planetary embryos collide with each other at speeds of kilometers per second, shattering and reforming, merging and growing in impacts so energetic that they can melt entire worlds. The collision that formed Earth's moon, the impact between the proto-Earth and a Mars-sized body called Theia, roughly 4.5 billion years ago, is perhaps the most famous example of this process, but it was far from unique. Such collisions were commonplace in the early solar system, and in every young planetary system throughout the galaxy. But not every gravitational encounter between planetary embryos leads to a collision. Sometimes, when two massive bodies pass close to each other, the gravitational interaction does not result in a merger, but in a dramatic exchange of energy and momentum. One body gains orbital energy, moving to a higher, more distant orbit. The other loses orbital energy, falling to a lower, closer orbit. This process is called gravitational scattering, and it is one of the most important mechanisms for producing rogue planets. If the energy exchange is large enough, the outward scattered body can be given enough velocity to exceed the escape velocity of the entire solar system. It is flung outward, past the orbits of the outermost planets, past the icy reaches of the Kuiper Belt equivalent, past the tenuous boundary where the star's gravity can no longer hold it, and into interstellar space. A planet has become a rogue. Planet-planet scattering is not a marginal process. Simulations conducted by researchers such as Dimitri Veris of the University of Warwick and Sean Raymond of the Laboratoire d'Astrophysique de Bordeaux have shown that it is an extremely common outcome of solar system formation. In many simulations, systems that begin with 4, 5, or 6 giant planets end up with only 2 or 3, the rest having been ejected through gravitational interactions. The ejected planets carry with them a record of the chaos they experienced, their final velocities encoding information about the masses and orbits of the planets that expelled them. Some are ejected gently with velocities just barely above escape speed, and they drift away from their parent star slowly, potentially remaining in the general neighborhood of their birth for millions of years before the gravitational influence of the galaxy itself carries them away. Others are ejected violently at speeds of 10 or 20 kilometers per second, and they rocket out of their solar system and into the void, never to return. One of the most compelling pieces of evidence that planet-planet scattering is widespread comes from the study of exoplanetary systems, planetary systems around other stars. When astronomers began discovering exoplanets in large numbers in the late 1990s and early 2000s, they were startled by how different many of these systems were from our own. Many exoplanets were found on highly elliptical orbits, elongated paths that took them swooping close to their star and then far away. Nothing like the nearly circular orbits of the planets in our solar system. These eccentric orbits are a natural signature of gravitational scattering. When planets interact and scatter off each other, the surviving planets are often left on eccentric orbits, their paths permanently distorted by the close encounters that ejected their siblings. The prevalence of eccentric exoplanet orbits tells us that scattering events are not rare. They are a fundamental part of how planetary systems evolve. Our own solar system may not be immune to this process. The Nice model, named after the city of Nice in France where it was developed by a team of researchers including Hal Levison, Alessandro Morbidelli, Rodney Gomez, and Cleomenes Tsiganis, proposes that the outer solar system underwent a dramatic reorganization roughly 4 billion years ago. In the original version of the model, published in 2005, the 4 giant planets, Jupiter, Saturn, Uranus, and Neptune, were initially in a more compact configuration than they occupy today. all orbiting closer to the Sun and closer to each other. Beyond them lay a massive disk of icy planetesimals, the remnants of the solar system's formation. Gravitational interactions between the giant planets and this disk caused the planets to migrate, with Jupiter moving slightly inward and Saturn, Uranus, and Neptune moving outward. At some point, Jupiter and Saturn crossed a critical orbital resonance, a configuration where Saturn's orbital period was exactly twice that of Jupiter, and the resulting gravitational perturbation destabilized the entire outer solar system. What followed, according to the NICE model, was a brief but intense period of chaos. Uranus and Neptune were scattered outward by close encounters with Saturn and Jupiter, plowing through the outer planetesimal disk and scattering its contents throughout the solar system. This scattering event is thought to be the cause of the late heavy bombardment, a period of intense cratering that scarred the surfaces of the Moon, Mercury, Mars, and Earth roughly 3.9 billion years ago. The model explains many features of the solar system that were previously puzzling, including the current orbits of the giant planets, the structure of the Kuiper Belt, and the existence of the Trojan asteroids that share Jupiter's orbit. But some versions of the NICE model go further. They suggest that the early solar system may have contained a fifth giant planet, an ice giant similar to Uranus or Neptune, that was ejected entirely during the instability. This hypothetical planet, sometimes informally called Planet 5, would have been scattered by Jupiter or Saturn into an orbit so elongated that it escaped the Sun's gravity altogether and became a rogue planet. If this is true, then our own solar system, the one we call home, the one that gave rise to life on Earth, may have contributed a rogue planet to the galaxy's wandering population. Somewhere out there, perhaps tens or hundreds of light years away by now, a world that was born alongside Earth and Mars and Jupiter may be drifting through the interstellar void, carrying frozen memories of the Sun it lost 4 billion years ago. Planet-planet scattering during formation is not the only way a planet can be separated from its star. Another mechanism involves the gravitational influence of other stars, particularly in the dense stellar environments where most stars are born. The majority of stars in the galaxy do not form in isolation. They form in clusters, groups of hundreds or thousands of stars all born from the same molecular cloud, all crowded together in a relatively small volume of space. In these dense birth environments, close encounters between stars are common. When two stars pass close to each other, the gravitational interaction can be powerful enough to strip planets from one or both of the passing systems. A planet that was peacefully orbiting its star at a distance of, say, 30 astronomical units might suddenly find itself caught in a gravitational tug-of-war between its parent star and a passing interloper. If the encounter is close enough and the passing star is massive enough, the planet can be torn from its orbit and sent wandering into space. Simulations of young star clusters by researchers such as Simon Portuguese Zwart of Leiden University have shown that stellar encounters can be remarkably effective at liberating planets. In dense clusters, where stars are separated by distances of only a few thousand astronomical units, a significant fraction of outer planets can be stripped away during the first few million years, before the cluster dissolves and its member stars drift apart into the general galactic population. The planets that are most vulnerable to this process are those in wide orbits, far from their parent star, where the gravitational bond is weakest. Inner planets, orbiting close to their star, are relatively safe. But a planet orbiting at the distance of Neptune or beyond is living on borrowed time in a dense cluster environment. Sooner or later, a stellar encounter will come close enough to set it free. There is also the question of what happens to planets when their star dies. Stars do not live forever. They burn through their nuclear fuel over timescales that depend on their mass, from a few million years for the most massive stars to trillions of years for the smallest red dwarfs. When a star like our Sun exhausts the hydrogen fuel in its core, it undergoes a series of dramatic transformations. It swells into a red giant, expanding to hundreds of times its original radius, engulfing the inner planets and flooding the remaining planets with intense radiation and stellar wind. It then sheds its outer layers in a series of thermal pulses, losing a substantial fraction of its mass in the form of a planetary nebula, that beautiful shell of glowing gas that surrounds the dying star. What remains is a white dwarf, a dense, Earth-sized remnant containing roughly half the mass of the original star. This mass loss has profound consequences for any surviving planets. When a star loses mass, its gravitational pull weakens, and the orbits of its planets expand in response. If the mass loss is slow and gradual, as it typically is during the red giant and asymptotic giant branch phases, the planets simply drift outward to wider orbits, maintaining stable, if more distant, paths around the white dwarf. But if the mass loss is sudden, as can happen in certain types of stellar explosions, the planetary orbits can be destabilized entirely. Moreover, even gradual mass loss can push planets that were already in wide orbits past the point of no return. A planet orbiting at 50 astronomical units around a star that loses half its mass may find that its new orbit is no longer bound. It drifts away, slowly, gently into interstellar space. Not flung violently, but released, like a balloon slipping from a child's hand on a windless day. For the most massive stars, the end is far more dramatic. Stars, more than roughly 8 times the mass of the Sun, end their lives not as white dwarfs, but as supernovae, catastrophic explosions that can briefly outshine an entire galaxy. In a supernova, the star ejects most of its mass in a single, violent event lasting only seconds. The sudden loss of nearly all the star's mass means that any surviving planets are almost certainly unbound. They are released instantaneously into space, carrying with them whatever velocity they had in their orbit at the moment of the explosion, plus any kick they receive from the asymmetric blast wave of the supernova itself. These planets are not gently released. They are hurled into the void at speeds that can reach tens or even hundreds of kilometers per second. They are among the fastest rogue planets in the galaxy, cosmic cannonballs fired by the death throes of giant stars. But there is yet another way that rogue planets can come into existence, and it challenges our very understanding of what a planet is. Some rogue planets may never have orbited a star at all. They may have formed in isolation, collapsing directly from small, dense clumps of gas in molecular clouds, in a process that mirrors star formation but at much lower masses. When a molecular cloud fragments during its collapse, most of the fragments are massive enough to form stars. But some fragments are smaller, containing only a few Jupiter masses of material, and they collapse into objects that are too small to ignite hydrogen fusion, too small even to be classified as brown dwarfs in some cases, but still massive enough to be considered planetary mass objects. These objects form alone, in the spaces between forming stars, and they drift into the galaxy as free-floating planets from the moment of their birth. This pathway to rogue planet formation was confirmed observationally in the early 2000s, when surveys of young star-forming regions like the Sigma Orionis cluster and the Orion Nebula cluster revealed populations of free-floating objects with estimated masses below the deuterium burning limit of roughly 13 Jupiter masses. The deuterium burning limit is often used as the dividing line between brown dwarfs and planets, although this boundary is somewhat arbitrary and not universally accepted. These objects were too young to have been ejected from solar systems by planet-planet scattering, as their host star-forming regions were only a few million years old, barely enough time for planetary systems to have fully formed, let alone to have undergone the gravitational instabilities that lead to ejection. The most natural explanation was that they had formed in situ, directly from the collapse of small gas cloud fragments, just as stars form from the collapse of larger fragments. More recently, observations with the James Webb Space Telescope have added a fascinating new dimension to this story. In 2023, a team of astronomers led by Samuel Pearson and Mark McCaugrian reported the discovery of what they called Jupiter mass binary objects, or jumbos, in the Orion Nebula. These are pairs of planetary mass objects, each with a mass of roughly 1 to 14 Jupiter masses, orbiting each other at separations of roughly 25 to several hundred astronomical units. The existence of these paired free-floating planets is difficult to explain through ejection, because it is extremely unlikely that two planets would be ejected from a solar system simultaneously and remain gravitationally bound to each other. Instead, the jumbos seem to support the idea that planetary mass objects can form directly from cloud fragmentation, just as binary stars form from the fragmentation of larger cloud cores. The jumbos are, in essence, the lowest mass binary systems ever observed, and their discovery has opened up new questions about the boundary between planet formation and star formation. The distinction between ejected rogue planets and free-floating planets that formed in isolation is important, because these two populations may have very different properties. An ejected planet carries with it the chemical and structural signature of the protoplanetary disk in which it formed. It has a core of heavy elements, built up through the accretion of planetesimals. It may have a layered internal structure, with distinct shells of different composition, reflecting the complex processes of differentiation that occur as a planet cools and solidifies. A free-floating planet that formed through direct collapse, on the other hand, may have a composition much more similar to a star, dominated by hydrogen and helium with only trace amounts of heavier elements. It would lack the heavy element core that characterizes planets formed through core accretion. In principle, if we could study a rogue planet up close, we might be able to determine its origin by examining its composition and structure, reading the geological record of its birth like a detective piecing together the story of a crime. The total population of rogue planets in the galaxy is therefore a mixture of these different formation channels. Some were born around stars and ejected through planet-planet scattering. Some were torn from their stars by close stellar encounters in dense clusters. Some were released when their stars died and shed their mass. And some were never bound to a star at all, forming independently in the cold depths of molecular clouds. Each channel contributes a different fraction to the total population, and the relative contributions depend on factors that are still being studied and debated. What we do know is that the total number is enormous. The galaxy is awash in wandering worlds, and every one of them, regardless of how it came to be alone, is a testament to the complexity and violence and beauty of the processes that shape the cosmos. As you lie here, breathing slowly, feeling the gentle pull of sleep, consider this: the space between the stars. The space that looks so empty when you gaze up at the night sky is not empty at all. It is filled with worlds, frozen, silent, invisible worlds, each one carrying its own history, its own story of formation and loss and wandering. They are out there now, right now, passing through the darkness at speeds of kilometers per second, unaware of each other, unaware of us, unaware of anything at all. And yet they are as real as the ground beneath you, as real as the moon that pulls the tides, as real as any planet that has ever been given a name. They are the universe's hidden population, and their story is only beginning to be told. Section 3. Finding the Invisible. Now consider a challenge. Perhaps the most elegant and frustrating challenge in all of observational astronomy. You are looking for something that produces no visible light, something that orbits nothing, something that drifts through interstellar space in perfect, absolute silence, without a gravitational anchor, without a host star, without any of the usual signposts that tell astronomers where to point their telescopes. You are looking for a world that does everything in its power simply by existing, to remain invisible. This is the problem of finding rogue planets. And for most of the history of astronomy, it was not really a problem at all, because no one seriously believed they existed in large numbers. Planets were things that orbited stars. That was practically the definition. If it orbited a star, it was a planet. If it did not, it was something else, or it was nothing. The idea that billions or trillions of worlds might be drifting through the darkness between the stars, unattached to anything, glowing with no borrowed light, was not so much rejected as simply never considered. But the universe does not care about our definitions. And as our instruments grew sharper and our methods grew cleverer, the evidence began to accumulate. Something was out there. Many somethings. Worlds without suns, moving through the galaxy like ghosts. And the question became not whether they existed, but how on Earth, or rather how from Earth, you could find them. The answer, it turns out, was predicted over a century ago by a man who spent much of his career thinking about light and gravity. His name was Albert Einstein. In 1915, Einstein published his general theory of relativity, a framework for understanding gravity not as a force pulling objects together, but as a curvature of space and time caused by the presence of mass. Massive objects, stars, planets, galaxies, do not simply attract other objects. They bend. The fabric of space itself, and everything moving through that curved space, follows the contours of the curvature, light included. This was a radical idea. In Newton's universe, light traveled in straight lines. Period. But in Einstein's universe, light followed the curves of space-time, which meant that a beam of light passing near a massive object would be deflected, bent, redirected, not because anything was physically pushing the photons, but because the space through which they traveled was itself warped. Einstein worked out the math. He calculated exactly how much a ray of light would be bent as it passed near a massive body like the Sun. And in 1919, during a total solar eclipse, the British astronomer Arthur Eddington measured the positions of stars that appeared near the Sun's edge during the eclipse, and confirmed that their light had been deflected by almost exactly the amount Einstein predicted. The announcement made Einstein a global celebrity overnight. Space was curved. Light could be bent by gravity. The universe was stranger than anyone had imagined. But Einstein saw something else in his equations, something more subtle. If a massive object could bend light, then, under the right circumstances, it could act as a lens. Imagine a distant star shining steadily in the background. Now imagine a massive object, another star, a planet, anything with sufficient mass, passing directly between that distant star and an observer on Earth. The gravity of the intervening object would bend the light from the background star, curving it around itself from all sides. And if the alignment were precise enough, the light would be focused, concentrated. The background star would appear to brighten, sometimes dramatically, as if someone had turned up its dimmer switch for a few days or weeks. Einstein described this effect in a short paper published in 1936 in the journal Science. He called it gravitational lensing. But he was not optimistic about its practical usefulness. The alignment required was so precise, the chances of catching it so slim, that Einstein himself concluded the phenomenon would probably never be observed. He wrote that there was no great chance of observing this phenomenon. He was, as it turns out, spectacularly wrong. The specific type of gravitational lensing that would prove crucial for finding rogue planets is called microlensing. The prefix micro is important. In regular gravitational lensing, the lens is something enormous, a galaxy or a galaxy cluster, and the distortion produces dramatic arcs and rings of light visible in deep telescope images. But in microlensing, the lens is something much smaller. A single star, a brown dwarf, or, critically, a planet. And the effect is not a visible distortion of the background star's shape, because at stellar distances, neither the lens nor the source can be resolved as anything more than a point of light. Instead, the effect is a temporary brightening, a symmetric, smooth increase in the apparent brightness of the background star, rising to a peak and then fading back to normal as the lensing object drifts past. The beauty of microlensing is that it depends only on mass, not on light. The lensing object does not need to emit a single photon. It does not need to be visible at all. It only needs to have mass and to pass close enough to the line of sight between a background star and the observer. A completely dark, cold, invisible rogue planet drifting through interstellar space can produce a microlensing event just as readily as a glowing star can. The only difference is the duration and the shape of the light curve, and this is the key. The duration of a microlensing event is directly related to the mass of the lensing object. A star mass lens might produce a brightening event lasting weeks or months. A Jupiter mass object might produce one lasting a day or two. An Earth mass object might produce a brightening that lasts only a few hours. The lighter the lens, the shorter the event. And the shorter the event, the harder it is to catch. This means that finding rogue planets through microlensing requires an extraordinary kind of patience and an extraordinary kind of survey. You need to monitor millions of stars simultaneously, measuring their brightness over and over and over again, night after night, looking for that one star among millions that briefly, almost imperceptibly, gets a little brighter for a few hours before fading back to normal. You are looking for a needle in a haystack, except the needle appears for a few hours, flickers, and then vanishes forever. You will never see the same event again. Each detection is a one-time occurrence, unrepeatable and irretrievable. The first team to take on this staggering challenge in a systematic way was a group of astronomers based in Poland, led by a physicist named Andrzej Udalski at the University of Warsaw. Their project was called the Optical Gravitational Lensing Experiment, known by its acronym OGLE. It began in 1992, initially designed to search for dark matter in the form of massive compact halo objects, or MACHOs, by monitoring millions of stars in the dense star fields of the galactic bulge, the thick central region of the Milky Way, where stars are packed most closely together. The logic was elegant. If you stare at enough stars for long enough, eventually something will pass in front of one of them. If that something has mass, it will lens the background star, and you will see a brief, telltale brightening. The galactic bulge was the ideal target because it contains the highest density of background stars. The more stars you monitor, the higher your chances of catching a microlensing event. OGLE used a dedicated telescope at the Las Campanas Observatory in Chile, high in the Atacama Desert, one of the driest and clearest places on Earth. The telescope was equipped with a large mosaic CCD camera that could image wide swaths of the sky in a single exposure. Night after night, year after year, the telescope photographed the same dense star fields, building up an extraordinary record of the brightness of millions of individual stars over time. Udalski and his team developed sophisticated software to analyze these images automatically, measuring the brightness of each star in each frame and flagging any that showed the characteristic symmetric brightening of a microlensing event. Over the years, OGLE discovered thousands of microlensing events, becoming one of the most productive surveys in all of observational astronomy. The project went through multiple phases, each with upgraded cameras and improved sensitivity. OGL-4, which began in 2010, used a camera with a field of view of 1.4 square degrees and could monitor over 300 million stars in the galactic bulge simultaneously. The other major player in the microlensing search for rogue planets was the MOA collaboration, which stands for Microlensing Observations in Astrophysics. MOA was based at the University of Canterbury in New Zealand and operated a telescope at the Mount John Observatory on the shores of Lake Tekapo. Like OGLE, it monitored millions of stars in the direction of the galactic center. The two surveys were complementary, separated by enough longitude that between them they could cover a significant portion of each night, reducing the chances that a short-duration event would be missed because it happened during daylight hours at one site. This complementarity proved essential, because here is the cruel arithmetic of rogue planet detection. An Earth-mass rogue planet might produce a microlensing event lasting only a few hours. If your telescope can only observe for 8 or 10 hours per night, and the event happens to peak during your daytime, you miss it entirely. It is gone. It will never repeat. That particular alignment of rogue planet, background star, and observer will never occur. Again, not in the lifetime of the galaxy. Each event is a singular gift from geometry, and if you are not watching at the right moment, it is lost. Despite these challenges, the discoveries came, and some of them were remarkable. In 2011, the MOA and OGLE collaborations jointly analyzed a microlensing event designated MOA-2011-BLG-262. The light curve was unusual. It showed the primary brightening peak expected from a microlensing event, but it also showed a secondary anomaly, a small, brief, additional bump in brightness that could be explained by the presence of a companion to the lensing object. In other words, the lens was not a single body. It was a system of two objects. The analysis suggested two possible interpretations. Either the lens was a distant star with a Neptune-mass planet orbiting it, or it was a free-floating planet of roughly 4 Jupiter masses accompanied by a sub-Earth mass moon. The data could not definitively distinguish between these two scenarios, but the second possibility was electrifying. A rogue planet with a moon, a world wandering through the dark between the stars, and it was not alone. It had brought a companion with it, a tiny satellite clinging to its gravitational embrace as the pair drifted through the void together. We do not know, even now, which interpretation is correct. The microlensing event is over. The lens has moved on. There will never be a follow-up observation. That moment of alignment, those few days when the light curve revealed its secrets, was all we will ever get. And this is the particular heartbreak of microlensing. You see a shadow puppet on the wall, you can measure its shape, estimate its size, infer its nature. But you cannot pull back the curtain. The show is over as soon as it begins. But the possibility alone was enough to stir the imagination. A rogue planet with a moon, two worlds keeping each other company in the interstellar dark. If it is real, that moon is the loneliest place in the known universe. No star in the sky is close enough to cast shadows. No sunrise will ever break the horizon. The only light comes from the faint glow of the Milky Way above and perhaps, just perhaps, from the dim infrared warmth of its giant companion below. An even more tantalizing discovery came in 2020, when the OGLE team reported the detection of a microlensing event designated OGLE-2016-BLG-1928. This event was extraordinarily short. The brightening lasted only about 42 minutes. 42 minutes. That is shorter than an episode of television, shorter than a lunch break. In the vast sweep of cosmic time, it is less than nothing. But, in those 42 minutes, a faint background star in the galactic bulge brightened by a measurable amount, following the precise symmetric curve predicted by Einstein's equations. Something massive had passed between that star and the Earth, and, based on the duration of the event, that something was small. Very small. The team, led by Przemek Mroz, estimated that the lensing object had a mass comparable to that of Earth, perhaps a bit less, perhaps as low as the mass of Mars. This made it the smallest rogue planet candidate ever detected. Not a gas giant, not a mini Neptune. A rocky world, roughly the size of our own planet, drifting alone through the Milky Way with no star to call home. The paper was published in the Astrophysical Journal Letters in 2020, and it sent a quiet ripple through the astronomical community. If Earth-mass rogue planets could be detected, even rarely, even with such brief and unrepeatable events, then the techniques worked. The method was sound. All that was needed was more data, better instruments, and more patient watching. And there was something else in the data, something in the statistics. The number of short-duration microlensing events that OGLE and MOA were detecting was higher than expected. Not dramatically higher, but consistently, persistently higher than models predicted if rogue planets were rare. The events were there. The signals were there. The darkness between the stars was not as empty as it looked. But microlensing is not the only way to find rogue planets. There is another method, one that works through an entirely different physical principle, and it relies on a simple, almost poetic fact. Young planets are warm. When a planet forms, whether in a protoplanetary disk around a star, or through some more violent process of ejection or fragmentation, it retains the heat of its formation. The gravitational energy of its collapse, the kinetic energy of the countless impacts that built it, all of this is stored as thermal energy in its interior. A young gas giant, freshly formed and freshly ejected from its birth system, can have a surface temperature of over 1,000 degrees. It glows, not with visible light, not with the bright shine of a star, but with infrared radiation. Heat radiation. The kind of light your eyes cannot see, but that the right telescope, equipped with the right detectors, can detect from many light years away. This means that if a rogue planet is young enough, within the first 10 or 20 million years of its existence, it can be seen directly. Not through the subtle, fleeting signature of microlensing, but through its own intrinsic glow. You can photograph it. You can take its spectrum. You can study its atmosphere, measure its temperature, estimate its mass. It is, for a brief window of cosmic time, visible. The catch, of course, is that window of visibility. As the planet ages, it cools. The heat of formation radiates away into space. After 100 million years, the glow has faded significantly. After 1 billion years, it is essentially gone. The planet becomes dark, cold, and invisible to direct imaging. So this method only works for young rogue planets, and only in young stellar associations, the loose groupings of recently formed stars where planets would have been recently ejected. In December of 2021, a team led by Nuria Miret-Roig, a young astronomer at the University of Bordeaux in France, published a remarkable paper in the journal Nature Astronomy. Using data from the European Southern Observatory's Very Large Telescope in Chile, the Visible and Infrared Survey Telescope for Astronomy, the Canada-France-Hawaii Telescope, and the Subaru Telescope in Hawaii. Along with archival data from several space missions, her team had conducted the most extensive survey of rogue planet candidates in a single stellar association ever attempted. The target was the Upper Scorpius OB Association, a nearby region of recent star formation in the constellation Scorpius, located roughly 420 light-years from Earth. This region is young, roughly 5 to 10 million years old, which means any planets ejected during the turbulent early days of star formation would still be warm enough to detect in the infrared. Miret-Roig and her colleagues identified at least 70 rogue planet candidates in this region. 70, not one or two, not a handful. 70 free-floating planetary mass objects drifting through the association unbound to any star. Some were estimated to have masses of several Jupiter masses. Others were smaller, approaching the boundary between planets and brown dwarfs. 70 planets, wandering through a single star-forming region. And this was almost certainly an undercount, because the survey could only detect objects above a certain mass threshold. Smaller rogue planets, those with masses comparable to Neptune or Earth, would have been too faint to see. The real number could be many times higher. The darkness between the stars might be far more crowded than it appears. And yet, for all the progress that OGLE, MOA, and direct imaging surveys have made, we are still scratching the surface. Our current detection methods are limited. Microlensing catches only those rogue planets that happen to pass almost exactly in front of a background star as seen from Earth, a geometrically improbable alignment. Direct imaging catches only those rogue planets that are young and warm enough to glow in the infrared, a brief phase in a planet's life. The vast majority of rogue planets, the old, cold, dark ones that have been drifting for billions of years, remain completely invisible to us. This is about to change, and the instrument that will change it has a name. It is called the Nancy Grace Roman Space Telescope, named after Nancy Grace Roman, the astronomer who is often called the mother of the Hubble Space Telescope for her pioneering role in developing NASA's space astronomy program. The Roman Space Telescope is scheduled to launch around 2027, and among its many scientific goals, one stands out as particularly transformative for rogue planet science. Roman will conduct a massive gravitational microlensing survey of the galactic bulge, monitoring hundreds of millions of stars continuously from the stable, unblinking vantage point of space. Unlike ground-based telescopes, Roman will not lose time to weather, to daylight, to atmospheric turbulence, or to the rotation of the Earth. It will stare at the same patch of sky without interruption for months at a time, capturing every flicker, every brightening, every 42-minute event that a ground-based telescope might miss because a cloud rolled in at the wrong moment. The telescope's infrared detectors are far more sensitive than anything currently available on the ground. Its wide-field instrument can image a field of view 100 times larger than Hubble's, allowing it to monitor a staggering number of background stars simultaneously. And its position in space, above the blurring and distorting effects of Earth's atmosphere, means its measurements will be sharper and more precise than any ground-based microlensing survey has ever achieved. Current estimates suggest that the Roman Space Telescope's microlensing survey could detect thousands of rogue planets, not dozens, not hundreds, thousands, and crucially, it will be sensitive to masses far below what current surveys can reach. Roman should be able to detect rogue planets down to the mass of Mars, or even smaller. For the first time, we will have a genuine statistical census of free-floating planets in the Milky Way. We will know not just that they exist, but how many there are, what their mass distribution looks like, and how they compare in number to the planets that remain bound to stars. Roman will not be alone. The European Space Agency's Euclid mission and the Vera C. Rubin Observatory in Chile will contribute complementary datasets, each covering different areas of the sky with different sensitivities. Together, these instruments will give us our first comprehensive view of the rogue planet population. We are entering a new era. For decades, rogue planets existed primarily as theoretical curiosities. Now they are becoming an observational reality. The invisible is becoming visible. The silent is beginning to speak. But there is one thing that will never change about microlensing, no matter how good our instruments become. Each detection is a single, fleeting glimpse. A rogue planet drifts across the line of sight to a distant star. The star brightens for a few hours or days, and then the alignment dissolves. The rogue planet moves on. The background star returns to normal, and you are left with a light curve, a mathematical shape drawn in photons that tells you something was there but can never tell you exactly what. You cannot go back. You cannot follow up. You cannot point a bigger telescope at the same spot and look again, because there is nothing left to see. Every rogue planet detection through microlensing is a farewell, a single handshake in the dark. You glimpse a world for a moment. You measure what you can, and then it is gone forever, swallowed by the vast, patient darkness between the stars. Section 4. A Census of Darkness. How many rogue planets are there in our galaxy? This is one of those questions that sounds simple and turns out to be staggeringly difficult to answer. But let us try. Let us follow the evidence wherever it leads, from the earliest estimates to the latest calculations, and see if we can put a number on the darkness. The first serious attempt to census the rogue planet population came in 2011, in a landmark paper led by Takahiro Sumi of Osaka University and published in the journal Nature. Sumi and his colleagues analyzed 2 years of microlensing data from the MOA2 survey, which had monitored roughly 50 million stars in the direction of the galactic bulge. They were looking specifically for short-duration microlensing events, the kind produced by objects significantly less massive than a typical star. What they found was startling. After carefully filtering out events caused by known stars and stellar remnants, they identified a population of short timescale microlensing events that could not be explained by known stellar populations alone. Something else was out there, and there was a lot of it. Based on the frequency of these short events and detailed statistical modeling of the Milky Way's stellar and planetary populations, Sumi and his co-authors estimated that there were roughly 1.8 Jupiter-mass rogue planets for every main sequence star in the galaxy. Let that number settle for a moment. Nearly 2 free-floating Jupiter-mass planets for every star. The Milky Way contains somewhere between 200 billion and 400 billion stars. If the Sumi et al. Estimate was correct, it meant there were at least 360 billion to 720 billion rogue Jupiters wandering through our galaxy. More rogue Jupiters alone than there are stars. And that was only counting the Jupiter mass population. Smaller rogue planets, the Neptunes, and super-Earths and Earths were not included in that estimate because the survey was not sensitive enough to detect them reliably. The paper was published in May 2011, and the reaction was immediate. It was one of those results that, if confirmed, would fundamentally alter our understanding of planetary formation and the architecture of the galaxy. The idea that planets could outnumber stars was not entirely new as a theoretical possibility, but seeing it spelled out in real data, with real numbers and real statistical confidence, was something else entirely. But science is a process of refinement, not declaration, and the Sumi et al. Result immediately drew scrutiny. The most significant concern was a subtle but important one. How do you distinguish, in a microlensing light curve, between a truly free-floating rogue planet and a planet that is simply on a very wide orbit around a distant star? This is not a trivial question. A planet orbiting its host star at, say, 500 astronomical units would be so far from its parent star that, for the purposes of a microlensing event lasting a few days, it would look identical to a free-floating planet. It would be moving through space more or less independently during the event. Its host star would be far enough away that it would produce no detectable signal in the light curve. The microlensing method, powerful as it is, cannot easily tell the difference between a planet that has no star and a planet that has a very distant star. This distinction matters enormously. If many of the short-duration events that Sumi and colleagues attributed to rogue planets were actually caused by wide-orbit-bound planets, then the true number of rogues would be much lower. The galaxy might not be swarming with free-floating Jupiters after all. It might instead be swarming with planets on extraordinarily wide orbits, which would be a fascinating finding in its own right, but a very different one. Several independent studies in the years following the 2011 paper explored this ambiguity. Some researchers argued that the Sumi et al. Estimate was likely an overcount. Simulations of planet formation and dynamical ejection suggested that producing nearly 2 rogue Jupiters per star was extremely difficult. The known ejection mechanisms, gravitational scattering during the chaotic early days of a planetary system, close encounters with passing stars, interactions during the dissolution of stellar clusters, could certainly produce rogue planets, but producing them in such enormous numbers required extreme assumptions. Other researchers pointed out that the mass function of rogue planets was highly uncertain. The Sumi et al. Analysis assumed a specific relationship between event duration and lens mass. But this relationship depends on the velocity distribution of the lenses and the sources, which is itself uncertain. Small changes in these assumptions could produce significantly different population estimates. The debate was constructive, not contentious. This is how science works at its best. A provocative result is published. Others test it, question it, poke at its assumptions. The result is refined, corrected, and either confirmed or revised. And, in this case, revision was clearly needed. The revision came in 2023, when Takahiro Sumi and his colleagues published an updated analysis. This new study used a dramatically improved dataset, 9 years of MOA2 observations covering over 6,000 microlensing events, compared to the roughly 500 events in the original 2011 analysis. The statistical power was far greater. The systematic uncertainties were better understood, and the results told a more nuanced story. The updated analysis found that the number of Jupiter-mass rogue planets was significantly lower than the 2011 estimate. Instead of nearly 2 per star, the new data suggested roughly 0.4 Jupiter-mass rogue planets per star. Still a substantial number. Still hundreds of billions across the galaxy, but a factor of 4 or 5 lower than the original headline figure. However, the updated study found something else. When the researchers extended their analysis to shorter duration events, probing lower masses, the numbers went up dramatically. The data suggested that as you move from Jupiter mass rogues to Neptune mass rogues to Earth mass rogues, the population increases steeply. For every free-floating Jupiter, there appear to be many more free-floating Neptunes. For every free-floating Neptune, many more free-floating Earths. The mass function of rogue planets appears to rise sharply toward lower masses. This is exactly what theoretical models of planetary ejection predict. In a young planetary system, where multiple planets are jockeying for stable orbits, the smallest planets are the easiest to eject. A close gravitational encounter between a Jupiter-mass planet and an Earth-mass planet in the same system is not a fair fight. The massive planet barely flinches. The small planet is flung outward, often at escape velocity, and is lost to interstellar space forever. The bigger planets tend to stay. The smaller planets tend to go. This mass-dependent ejection creates a very specific signature in the rogue planet population. The smallest worlds should be the most numerous. And the data, tentative as it still is, appears to confirm exactly this pattern. So let us try to assemble the numbers, keeping in mind that all of these estimates carry significant uncertainties and will be refined dramatically in the coming decade as the Roman Space Telescope and other surveys begin their work. For Jupiter-mass rogue planets, the current best estimate is roughly 0.4 per star, give or take. With perhaps 300 billion stars in the Milky Way, that gives us something like 120 billion free-floating Jupiters. 120 billion gas giants, each one a massive world of swirling hydrogen and helium, each one drifting alone through the interstellar medium with no sun to warm it and no system to call home. For Neptune-mass rogue planets, the estimates become more uncertain, but the population is believed to be several times larger than the Jupiter-mass population. Perhaps 1 or 2 per star. That would put the number somewhere between 300 billion and 600 billion free-floating ice giants. And for Earth mass and sub-Earth mass rogue planets, the numbers become truly staggering. Some estimates extrapolating from the observed mass function and from theoretical models of planetary system dynamics suggest that there could be 10 or more Earth mass rogue planets for every star. Perhaps even 20. That would mean trillions, not billions, trillions. Somewhere between 2 trillion and 6 trillion small, rocky, frozen worlds drifting through the Milky Way alone. Worlds the size of Earth, worlds the size of Mars, worlds the size of the Moon, an inconceivable multitude of dark, silent, wandering bodies, vastly outnumbering the stars themselves. If you add all of these populations together, from the gas giants to the smallest rocky fragments, the total number of rogue planets in the Milky Way may be somewhere between 5 trillion and 20 trillion. The uncertainty is large, and it will remain large until the next generation of surveys provides better data. But even the lowest credible estimate puts the number in the trillions. Trillions. Let us take a moment to appreciate what this means for the structure of our galaxy. We tend to think of the Milky Way as a collection of stars. 400 billion stars arranged in a great spiral disk, with a central bulge and a halo of old stars and globular clusters. And of course, it is that. But if the rogue planet estimates are even approximately correct, then the Milky Way is also, and perhaps more fundamentally, a collection of planets. Dark planets, cold planets, invisible planets, planets that outnumber the stars by a factor of 10 or 20 or more. In a very real sense, the stars are the minority. They are the bright, conspicuous, attention-getting minority in a galaxy dominated by dark, silent worlds. When you look up at the night sky and see the Milky Way stretching from horizon to horizon, you are seeing the stars. But for every star you see, there may be 20 worlds you cannot see, drifting invisibly through the same space, sharing the same galaxy, obeying the same gravitational laws, but emitting no light, reflecting no light, and revealing their presence to no one. This is a profound shift in perspective. For centuries, we have mapped the galaxy in starlight. Our charts and atlases are maps of luminous objects. But a true map of the Milky Way, one that showed everything, would be dominated not by stars, but by planets, a vast, dark, teeming multitude of worlds without suns. What does this mean for the total mass budget of the galaxy? Less than you might think. Even trillions of Earth-mass planets add up to a relatively modest amount of mass compared to the galaxy's total. An Earth-mass planet is about 1/300,000th the mass of the Sun. So even 6 trillion Earth-mass rogues would have a combined mass equivalent to only about 20 million solar masses, which is a tiny fraction of the Milky Way's total stellar mass of roughly 50 billion solar masses. Jupiter-mass rogues contribute more per individual, but there are far fewer of them. In total, the rogue planet population probably adds less than 1% to the galaxy's overall mass budget. They are not a significant source of dark matter. They are not a major gravitational influence on the galaxy's structure. In terms of mass, they are almost negligible. But in terms of number, they dominate. And in science, number matters. Each of those trillions of worlds is a physical object with a surface, an interior, a history, and a set of physical conditions unlike any other. Each one formed somewhere, was shaped by some set of processes, and carries within it a record of the conditions in which it was born. The sheer number of rogue planets means that the diversity of planetary conditions in the galaxy is far richer than we ever imagined when we thought of planets only as things that orbit stars. Now, let us extend this thinking beyond our own galaxy. The Milky Way is one galaxy among roughly 200 billion to 2 trillion in the observable universe. If even a fraction of these galaxies has a rogue planet population comparable to ours, the total number becomes almost meaningless in its scale. 200 sextillion, perhaps. That is 2 followed by 23 zeros. And the observable universe is almost certainly not the entire universe. The total number of rogue planets in all of creation may be beyond calculation, beyond meaning. The rogue planet census suggests something profound about the galaxy we live in. The majority of planets, in the Milky Way and perhaps in the universe, do not belong to anyone. They are not part of any system. They have no star, no orbit, no fixed address. Our solar system, with its 8 planets orbiting a single stable star, is not the typical planetary arrangement. It is the unusual one, the rarity. Most planets in the universe may never see a sunrise. Most planets may drift through the darkness for their entire existence, from formation to final cooling, without ever being part of a system that an astronomer could point to on a chart and say, "There, that is an address." The galaxy is not mostly empty. We have said this before, but it bears repeating because it runs counter to one of the deepest intuitions we have about space. We think of interstellar space as void, as vacuum, as nothingness. And in terms of density, it is. The average density of interstellar space is roughly 1 atom per cubic centimeter. That is emptier than the best vacuum we have ever created in a laboratory on Earth. But scattered through that emptiness are trillions of worlds, cold, dark, silent worlds. Worlds with iron cores and rocky mantles. Worlds with thick atmospheres of hydrogen and helium. Worlds with frozen oceans of water or methane or ammonia. Worlds that were born in the light and warmth of a protoplanetary disk, and then cast out into the darkness by the gravitational chaos of their siblings. And perhaps the most remarkable thing about this census is what it reveals about the process of planet formation itself. If the galaxy produces trillions of rogue planets, then planet formation is not a tidy, efficient process that neatly slots every world into a stable orbit. It is a messy, violent, wasteful process that creates far more planets than any stellar system can hold. Most of the worlds that form around young stars are eventually thrown away, discarded, ejected, lost. Think of it as a kind of cosmic overproduction. A young star forms with a disk of gas and dust. From that disk, dozens or perhaps hundreds of planetary embryos begin to coalesce. They grow by accreting material. They interact gravitationally. They migrate inward and outward through the disk. And as they do, they interfere with each other. Close encounters scatter smaller bodies onto eccentric orbits. Some collide and merge. Others are flung outward, gaining enough velocity to escape the star's gravitational pull entirely. By the time the system settles into its final configuration, perhaps after 10 million or 100 million years of chaos, only a handful of planets remain on stable orbits. The rest are gone, ejected into interstellar space, and each of those ejected planets becomes a rogue, carrying with it the chemical fingerprints of the disk in which it formed but owing allegiance to no star. This picture of planet formation as a violent, selective, and profoundly wasteful process is one of the major insights of modern planetary science. We used to think of planetary systems as the natural, efficient products of star formation. Now we understand them as the survivors of a brutal winnowing. The planets that remain in orbit are the winners of a gravitational competition. The rogue planets are the losers. But there are many more losers than winners. Let us pause here in the darkness and think about what all of this means together. The galaxy is full of wanderers, trillions of them, worlds of every size, from gas giants larger than Jupiter to rocky fragments smaller than the Moon. They drift through interstellar space at speeds of tens of kilometers per second, following long, slow, looping paths through the galaxy's gravitational field. Some travel alone. Some may travel in pairs or small groups, gravitationally bound to each other but to nothing else. They pass through the spiral arms and through the gaps between the arms. They rise above the galactic plane and sink below it. They have been drifting for billions of years, and they will continue drifting for billions more, long after the stars that formed alongside them have exhausted their fuel and died. They carry no light. They emit no signal. They announce their presence to no one. And yet they are there, in numbers that defy comprehension. A hidden population so vast that it transforms our understanding of what a galaxy actually is. Not just a collection of stars, not just a web of gas and dust and dark matter, but also, and perhaps above all, a sea of dark, cold, wandering worlds. This is the census of darkness, and it is far from complete. The Roman Space Telescope will refine these numbers. Future missions will push the sensitivity to even lower masses, to rogue moons and rogue asteroids and rogue fragments of shattered worlds. The more we look, the more we find. And the more we find, the clearer it becomes that the universe's favorite kind of planet is one that belongs to no one. A world without a sun. A planet without a home. And somewhere out there, in the vast, cold, silent darkness between the stars, trillions of these worlds are drifting right now. As you lie here, as you listen to these words, as the weight of the day fades and sleep draws closer, they are out there, unseen, uncounted, unknown, worlds beyond number, moving through the dark in absolute silence, each one a place, each one a world, each one as real as the ground beneath you. The galaxy is not empty. It only looks that way because we can only see the things that shine. Section 5. Life in Eternal Night. Let us pause here and ask a question that may seem absurd at first. Could anything be alive on one of these worlds? Could life, real biological life, exist on a planet that has no star? The question sounds almost like a contradiction. We are taught from childhood that life depends on the sun. Plants grow toward sunlight. Food chains begin with photosynthesis. The sun warms the oceans, drives the weather, powers the entire biosphere. Without a star, there's no light, no warmth, no energy. Without a star, a planet is just a frozen rock hurtling through the void. Surely nothing could survive on such a world, but that assumption, as deeply held as it is, may be wrong. And the evidence that it is wrong does not come from some distant theoretical calculation. It comes from places right here in our own solar system. Places that have quietly been rewriting our understanding of where life can exist. Consider Europa, one of the 4 large moons of Jupiter, first observed by Galileo in 1610. From a distance, Europa looks like a smooth, pale marble, its surface covered in a shell of ice that may be 10 to 30 kilometers thick. The surface temperature hovers around minus 160 degrees Celsius. It is one of the coldest places in the solar system. And yet, beneath that ice, there is an ocean. A vast global ocean of liquid salt water, estimated to contain roughly 2 to 3 times the volume of all the water in Earth's oceans combined. An ocean that has existed for billions of years. An ocean that is, right now, as you listen to these words, sloshing and churning in total darkness beneath a ceiling of ice, more than 780 million kilometers from the sun. How is this possible? How can liquid water exist so far from any source of warmth? The answer is tidal heating. Europa orbits Jupiter in a slight ellipse, and as it moves closer and then farther from the giant planet, Jupiter's immense. Gravity flexes and stretches the moon's interior. This constant kneading generates friction, and friction generates heat. It is the same principle that warms your hands when you rub them together, but scaled up to a planetary body. The gravitational interaction between Europa, Jupiter, and the neighboring moons Io and Ganymede creates a resonance that keeps Europa's orbit slightly eccentric, ensuring that the tidal heating never stops. The result is an ocean that has remained liquid for billions of years, heated not by a star but by gravity itself. Now consider Enceladus, a tiny moon of Saturn, barely 500 kilometers across. You could fit it comfortably inside the borders of France. It is so small that most astronomers paid it little attention until the Cassini spacecraft arrived at Saturn in 2004. And then everything changed. Cassini discovered something extraordinary. Near the south pole of Enceladus, huge plumes of water vapor and ice particles were erupting through cracks in the surface, shooting hundreds of kilometers into space. The moon was venting its interior ocean directly into the vacuum of space. And when Cassini flew through those plumes and analyzed their composition, it found something remarkable. Molecular hydrogen, silica nanoparticles, complex organic molecules, salts. The molecular hydrogen was particularly significant. On Earth, molecular hydrogen is produced at hydrothermal vents on the ocean floor, where superheated water reacts with iron-rich rock in a process called serpentinization. The presence of molecular hydrogen in the plumes of Enceladus strongly suggests that similar hydrothermal activity is occurring at the bottom of its ocean. Hot water meeting hot rock in the dark. And on Earth, hydrothermal vents are not just chemically interesting. They are teeming with life. Tube worms, shrimp, bacteria, entire ecosystems that have never seen a single photon of sunlight. These organisms derive their energy not from light, but from chemistry, from the chemical gradients created by hot, mineral-rich water mixing with cold seawater. This process is called chemosynthesis, and it is completely independent of the sun. Here, then, is a profound realization. 2 worlds in our own solar system, Europa and Enceladus, have liquid water, chemical energy, and the organic building blocks of life. They have had these things for billions of years, and none of it depends on the sun. None of it requires a star at all. Now extend this reasoning to a rogue planet, a world drifting through interstellar space, far from any star. At first glance, such a planet seems like the most inhospitable place imaginable. Its surface would be frozen solid, perhaps hundreds of degrees below zero. Any atmosphere would have condensed into frost. the planet would be a dark, silent ball of ice and rock. But beneath that frozen surface, things could be very different. A rocky planet of sufficient size, say Earth mass or larger, contains a substantial amount of radioactive material. Uranium-238, thorium-232, potassium-40. These elements were forged in ancient supernova and incorporated into the planet during its formation. And they are unstable. Over billions of years, they undergo radioactive decay, releasing energy in the process. This is not a trivial amount of energy. On Earth, radioactive decay in the mantle and crust generates roughly 20 terawatts of heat, accounting for roughly half of the planet's total internal heat production. The other half comes from primordial heat, the residual thermal energy left over from Earth's formation and the giant impact that created the Moon. Together, these heat sources drive plate tectonics, power volcanic activity, and maintain Earth's liquid iron core. A rogue planet would lose its primordial heat more quickly without the insulating warmth of a nearby star. But radioactive decay is a slow, steady process. Uranium-238 has a half-life of roughly 4.5 billion years. Thorium-232 has a half-life of roughly 14 billion years. These elements will continue generating heat for tens of billions of years, far longer than the current age of the universe. This means that a sufficiently large rogue planet could maintain a liquid water ocean beneath its frozen surface for an extraordinarily long time. Not millions of years, not hundreds of millions, but billions of years, perhaps tens of billions. An ocean sustained not by starlight, but by the quiet, patient energy of atomic nuclei falling apart, one by one, deep within the planet's rocky interior. And if that ocean sits atop a rocky mantle, if there is hot rock in contact with liquid water, then the same hydrothermal chemistry that occurs at the bottom of Earth's oceans could occur there too. Chemical energy, mineral gradients, warm water and cold water mixing. All the ingredients that chemosynthetic life requires. The possibility is extraordinary. A rogue planet, alone in the dark between the stars, could harbor a living ocean beneath its ice. An entire biosphere, thriving in permanent darkness, powered by the decay of elements that were created in the death throes of stars that exploded billions of years before the planet even formed. In 1999, the planetary scientist David Stevenson published a remarkable paper in the journal Nature. Stevenson, a professor at the California Institute of Technology and one of the world's leading experts on planetary interiors, proposed a scenario that was even more provocative than subsurface oceans. He argued that under the right conditions, a rogue planet could maintain liquid water not just beneath its surface, but on its surface, out in the open, without a star. The key ingredient was hydrogen, not water, not carbon dioxide, but molecular hydrogen, the lightest and most abundant element in the universe. Stevenson's reasoning went like this. When a planet forms in a protoplanetary disk, it can capture a substantial atmosphere of hydrogen and helium from the surrounding gas. Most rocky planets close to their star eventually lose this hydrogen atmosphere because stellar radiation strips it away. But a planet that is ejected early from its solar system, before the star has had time to strip its atmosphere, could retain a thick envelope of molecular hydrogen. And molecular hydrogen has an unusual property. It is nearly transparent to visible light, meaning it does not absorb much incoming radiation. But it is an effective absorber of infrared radiation, the thermal energy that a warm planet radiates back into space. In other words, molecular hydrogen is a greenhouse gas. This is different from the greenhouse effect we usually think about. On Earth, carbon dioxide and water vapor trap heat that originally came from the sun. But on a starless planet, the only source of heat is the planet itself, its own internal energy from radioactive decay and residual formation heat. A thick hydrogen atmosphere would act as a thermal blanket, trapping this internal heat and preventing it from radiating away into the cold of space. Stephenson calculated that a rogue planet with roughly Earth's mass and a hydrogen atmosphere with a surface pressure of roughly 100 to 1,000 times Earth's atmospheric pressure could maintain surface temperatures above the freezing point of water. Above 273 Kelvin, warm enough for liquid water to pool on the surface. Think about what this means. A planet with no star drifting through the absolute darkness of interstellar space could have rivers, lakes, perhaps even oceans. Not buried beneath kilometers of ice, but sitting on the surface under a thick, warm sky of hydrogen. Dark, yes, but warm and wet. The physics is straightforward. The hydrogen atmosphere acts as an insulating layer, trapping the planet's own heat the way a thick blanket traps the warmth of your body on a cold night. You do not need an external heat source. You are the heat source. The blanket just keeps it from escaping. Stephenson's paper was not science fiction. It was published in one of the most prestigious scientific journals in the world, and it was based on well-established physics of radiative transfer and atmospheric thermodynamics. The scenario is not guaranteed to occur, of course. It requires a specific set of initial conditions, a rocky planet of the right size, ejected at the right time, with the right atmospheric composition. But none of those conditions are physically impossible. And given the sheer number of rogue planets in the galaxy, estimated at billions or even trillions, even a small probability translates into an enormous number of worlds. Let us go deeper into this idea. What would such a world actually look like? Imagine standing on the surface of a Stephenson world. There is no sun in the sky. There is no sky at all in the way you are used to thinking about it. Above you is a thick, dense atmosphere of hydrogen, pressing down with enormous weight. The atmosphere is opaque, not because of clouds in the usual sense, but because of its sheer density. You cannot see the stars, but it is warm, perhaps 10 or 15 degrees Celsius, comfortable even. The ground beneath your feet might be rocky, volcanic, similar to the basaltic plains of Iceland or Hawaii. And there might be water, pools of it, streams fed by geothermal springs where hot water seeps up from the interior. The darkness would be total. No photon of starlight penetrates this atmosphere, and yet the world is not dead. Geothermal vents dot the landscape, releasing heat and minerals. Where water meets hot rock, chemical reactions occur, producing hydrogen sulfide, methane, ammonia, and other compounds that certain forms of life can metabolize. If life arose on such a world, it would be unlike anything we associate with biology on Earth's surface. There would be no photosynthesis because there is no light. Instead, all life would be chemosynthetic, feeding on the chemical energy provided by the planet's interior. The base of the food chain would not be plants or algae, but chemotrophic microorganisms, bacteria and archaea, that extract energy from chemical reactions between minerals and water. Could such life become complex? Could it evolve beyond simple, single-celled organisms? This is a harder question, and the honest answer is that we do not know. On Earth, the evolution of complex multicellular life was driven in part by the abundance of oxygen produced by photosynthetic cyanobacteria. Without photosynthesis, oxygen levels would remain low. And without oxygen, the energetic metabolism that powers a complex animal life would be difficult to sustain. But difficult is not the same as impossible. There are organisms on Earth that thrive without oxygen. Anaerobic bacteria and archaea have been found in some of the most extreme environments on our planet, and on a rogue world with billions of years of chemical evolution. Who can say what might emerge? Evolution is patient. Evolution is creative. And evolution does not require sunlight. The evidence that life can thrive without light is not hypothetical. It is real, it is documented, and it is far more extensive than most people realize. In the gold mines of South Africa, more than 3 kilometers below the surface, scientists have discovered thriving communities of bacteria in water-filled fissures in the rock. These organisms have been isolated from the surface for millions of years. They derive their energy from the radioactive decay of uranium in the surrounding rock, which splits water molecules and produces hydrogen. They are, in a very real sense, powered by nuclear energy. One species in particular stands out. In 2002, researchers reported the discovery of a bacterium called Desophorudis audaxviator, found 3 kilometers deep in a South African mine. This single species was the sole inhabitant of its ecosystem. No sunlight, no oxygen, no connection to the surface. It derived its energy entirely from radioactive decay. A complete, self-sustaining ecosystem consisting of a single species, powered by the same energy source that would be available on a rogue planet. Its name comes from Jules Verne's Journey to the Center of the Earth, and it means something like the bold traveler. Then there is Lake Vostok, buried beneath nearly 4 kilometers of Antarctic ice, sealed off from the surface for at least 15 million years. When researchers drilled down and retrieved water samples, they found microbial life, bacteria and archaea, alive and active, in water that has not seen the sun since before the genus Homo even existed. These are not marginal examples. The deep biosphere, the community of organisms living within Earth's crust, may contain as much biomass as all surface life combined. Life has been thriving in the dark for as long as life has existed. The sunlit surface is almost an afterthought. This brings us to one of the most profound conceptual shifts in modern astrobiology. For decades, the search for life beyond Earth has been organized around the concept of the habitable zone, the region around a star where temperatures are right for liquid water to exist on a planet's surface. This is sometimes called the Goldilocks zone. Not too hot, not too cold, but just right. But the habitable zone is defined by starlight. It assumes that the only source of energy that matters is a star. And what we have learned from Europa, Enceladus, the deep biosphere, and from Stephenson's theoretical work on hydrogen atmospheres is that starlight is not the only game in town. Tidal heating can maintain liquid water. Radioactive decay can maintain liquid water. A thick hydrogen atmosphere can trap enough internal heat to maintain liquid water. None of these mechanisms require a star. A rogue planet could have all of them. If this is true, then the concept of habitability needs to be radically expanded. The habitable zone is not a narrow ring around a star. It is everywhere that liquid water and chemical energy coexist, and that includes the vast, dark spaces between the stars, where billions or trillions of rogue planets drift in silence. The astronomer and astrobiologist Abel Mendez at the University of Puerto Rico has developed an index called the Earth Similarity Index, which rates planets on how similar they are to Earth. By this measure, most rogue planets score extremely low. But that index is calibrated to Earth's surface conditions, to a world bathed in starlight. If we recalibrate our thinking, if we ask not, how much does this world look like Earth's surface? But instead, could liquid water and chemical energy persist here for billions of years? The answer changes dramatically. The universe may be full of habitable worlds that look nothing like Earth, worlds with no sun, no sky, no photosynthesis, worlds where life, if it exists, has never known light, worlds that are habitable not because of their relationship to a star, but because of the energy locked within their own rock and the insulation of their own atmospheres. This is a humbling thought. We have spent decades scanning the habitable zones of other stars, looking for planets that resemble our own. And all the while, the most numerous habitable worlds in the galaxy may be the ones drifting in the spaces between the stars, invisible to our telescopes, hidden in the dark. There is one more idea worth exploring before we leave this topic. It is speculative, but it is grounded in real science, and it has implications that are almost too large to contemplate. The idea is panspermia, the hypothesis that life can be transported between worlds, hitching a ride on rocks blasted into space by asteroid impacts. We know this process occurs. When a large asteroid strikes a planet, the impact ejects debris at high velocity. Some of that debris reaches escape velocity and enters orbit around the Sun, or leaves the solar system entirely. We have found meteorites on Earth that originated on Mars, blasted off the Martian surface by ancient impacts, and eventually captured by Earth's gravity. The most famous of these is ALH84001, a Martian meteorite found in Antarctica in 1984, which briefly caused a sensation in 1996 when NASA scientists announced they had found possible microfossils within it. That claim remains controversial, but the fact that rocks travel between planets is not controversial at all. It is established science. Remarkably, some organisms might survive the journey. Bacterial endospores can endure extreme temperatures, vacuum, and radiation for extended periods. Experiments aboard the International Space Station have shown that bacterial spores can survive direct exposure to space for at least a year and a half. Now consider a rogue planet passing through a star system that harbors life. Debris from a living world floating in the system's Oort cloud could be captured by the rogue planet's gravity. Microorganisms embedded in rock fragments, landing on its frozen surface. Over geological time, those organisms might work their way through cracks in the ice to the liquid water below. They could take hold, begin to grow. And then, billions of years later, that same rogue planet might pass through another star system, another transfer of biological material. In this scenario, rogue planets become vectors of life, seeds drifting on the currents of galactic gravity, spreading biology across distances that no planet bound to a star could ever bridge. The astrobiologist Avi Loeb at Harvard has calculated that the rate of material exchange between star systems, while low for any single event, becomes significant when integrated over billions of years and trillions of objects. Let us sit with this for a moment. Let us consider what it means if even a fraction of these ideas are correct. If life can exist without starlight, then the habitable universe is not a scattering of warm, well-lit planets orbiting stable stars. It is vastly, almost incomprehensibly larger. It includes every rogue planet with a subsurface ocean, every drifting world with enough internal heat and the right chemistry. Worlds beyond counting, spread across every cubic light-year of every galaxy, in the enormous dark spaces between the stars where nothing seems to exist. We have been looking for life in all the lit places. Under the street lamp, as the old joke goes, because that is where the light is. But the dark places may be where most of life actually resides. The universe's true biosphere may not be the thin films of water on sunlit planets. It may be the hidden oceans, the deep rock, the warm interiors of wandering worlds that will never appear in any telescope's field of view. If life is common on rogue planets, then the number of living worlds in the galaxy increases by orders of magnitude, not by a factor of 2 or 10, but by a factor of thousands, perhaps millions. The galaxy would not be a sparse scattering of rare living worlds, separated by vast deserts of lifeless space. It would be saturated with life, soaked in it. Life everywhere, in every direction. Most of it hidden, most of it quiet, but alive. And here is the deepest implication of all. If life does not need stars, then life can outlast stars. Stars burn out. Our sun will exhaust its hydrogen fuel in roughly 5 billion years, swell into a red giant, and eventually fade into a white dwarf. In the very far future, all stars will die. The last red dwarfs will burn out in roughly 10 trillion years, and the universe will enter an era of darkness. But rogue planets will still be there. Their radioactive heat sources will continue to generate warmth for tens of billions of years. Their subsurface oceans may persist long after the last star has gone out. If life exists in those oceans, it may continue to exist. Quietly, patiently, in the dark. Life on rogue planets would be the last life in the universe. Not the bright, photosynthetic, oxygen-breathing life we know, but life nonetheless. Simple, ancient, enduring. The final inheritors of a cosmos that began with light and will end in darkness. And in that darkness, in some hidden ocean on some forgotten world drifting through the emptiness between dead galaxies, something will still be alive. Something will still be drawing energy from the decay of ancient atoms, still reproducing, still evolving, still carrying the thread of biology that began so long ago on worlds that have long since ceased to exist. That is a thought worth holding as you lie here tonight. The universe is not just large, it is deep, and in its deepest places, in the places we cannot see and may never visit, life may be more common, more enduring, and more resilient than we ever imagined. Section 6. The Loneliest Journey. Let us do something together now. Something that requires nothing more than your imagination. Close your eyes, if they are not already closed, and imagine that you are standing on the surface of a rogue planet. You are wearing some impossible suit that keeps you alive and warm, and you are standing on solid ground, and you are looking up. There is no sun. There has never been a sun. This world was born in chaos, flung from its home system billions of years ago, and it has been traveling through interstellar space ever since. It has no orbit, no year, no seasons. There is no sunrise and no sunset. There is no dawn and no dusk. There is no morning and no evening. There is only night. An eternal, unbroken night that began before the first humans walked upright on Earth and will continue long after our sun has burned out and gone cold. You might expect this to be terrifying, and perhaps it would be for a moment. The darkness is absolute. Beneath your feet, the ground is frozen. The temperature on the surface is somewhere around 200 degrees below zero. Any atmosphere this world once had has long since condensed into frost, a thin, brittle layer of frozen nitrogen or carbon dioxide dusting the rocks like snow. But then you look up, and what you see takes your breath away. The sky is full of stars, not dozens, not hundreds, but millions. The entire galaxy is spread above you in a great, blazing river of light, every star sharp and unwavering, because there is no atmosphere to blur them. On Earth, stars twinkle because their light passes through turbulent layers of air, refracting and shifting as the atmosphere moves. Here, there is no atmosphere. The stars do not twinkle. They burn with a hard, steady, crystalline clarity that no human being on Earth has ever seen with the naked eye. The Milky Way arcs overhead like a bridge made of light, its spiral arms visible not as a faint smudge but as a vast, detailed structure, dark dust lanes weaving between brilliant stellar nurseries. You can see the colors of individual stars, the hot blue-white of young, massive stars, the steady yellow of stars like our sun, the deep, warm orange and red of ancient low-mass stars that have been burning quietly since the galaxy was young. If you looked carefully enough, with the right instruments, you could pick out our sun. From the distance of a typical rogue planet wandering through the galaxy, our sun would be an unremarkable yellow dot, indistinguishable from billions of others. The pale blue dot of Earth would be utterly invisible, lost in the glare, a mote of dust circling a candle flame. But the sky itself would be glorious. The large and small Magellanic Clouds, satellite galaxies of the Milky Way, would be visible as bright, irregular patches of light. The Andromeda Galaxy, our nearest large galactic neighbor, would appear as a faint oval smudge, just as it does from Earth. 2.5 million light-years away, containing 1 trillion stars of its own. And there would be no light pollution. None. Not a single artificial photon anywhere in the sky. No horizon glow from distant cities, no satellites drifting overhead, no airplanes, no moon reflecting borrowed sunlight. Just the raw, unfiltered cosmos, spread from horizon to horizon in every direction. A sky so full of stars that the darkness between them feels less like emptiness, and more like the spaces between the notes in a piece of music. You would see nebulae with your bare eyes, the great clouds of gas and dust where stars are born, glowing faintly with the light of the young stars embedded within them. The Orion Nebula, if you happen to be in the right part of the galaxy, would be a wash of red and blue, visible to the naked eye as a complex, layered structure rather than the faint smudge it appears from Earth. This is the paradox of a rogue planet. It is one of the darkest places in the universe, and it offers one of the most magnificent views of the universe that any world could provide. Now let us come back down to the surface, back to the frozen ground and the absolute silence, because silence is the other defining quality of this world. On Earth there is always sound, wind in the trees, waves on the shore, the hum of insects, the distant rumble of thunder. Even in the quietest places there is the faint rush of blood in your ears, the beating of your heart. On a rogue planet with no atmosphere there is no sound at all. Sound requires a medium to travel through. In the near vacuum on the surface, nothing vibrates. No wind because there is no air. No weather because there is no atmosphere and no star to drive convection. It is a silence so complete that it has no equivalent in human experience. This world has been silent for billions of years, and it will be silent for billions more. But not all rogue planets are lifeless surfaces. Remember what we discussed in the previous section. Beneath that frozen exterior, there may be warmth, liquid water, chemical energy, perhaps even life. If you could somehow descend through the ice, through 10 or 20 or 50 kilometers of frozen water, you would eventually reach the ocean below. And there, the silence would break. Water carries sound beautifully, far better than air. If there were hydrothermal vents on the ocean floor, you would hear them. The hiss of superheated water meeting cold, the crack of rock shifting under thermal stress, the quiet, constant murmur of a world that is alive in its deep places even while its surface lies frozen and still. This is one of the strange and beautiful things about rogue planets. Their surfaces tell you almost nothing about what lies within. They are like old books with blank covers. The story is inside, hidden, waiting to be read by anyone patient enough to look beneath the surface. Now, let us think about what happens when a rogue planet does not stay in the empty spaces between the stars. What happens when one of these wandering worlds passes through a solar system? This is not a hypothetical scenario. It has almost certainly happened to our own solar system, and it will happen again. We know that interstellar objects pass through our solar system. In 2017, astronomers detected Oumuamua, the first confirmed interstellar object ever observed passing through our neighborhood. It was small, perhaps a few hundred meters across, tumbling end over end on a trajectory that clearly originated from outside the solar system. Its nature remains debated. Some suggested it was a fragment of a nitrogen ice planet. Others, most notably Avi Loeb, controversially proposed it might be an artificial object. Whatever it was, it demonstrated that interstellar objects regularly pass through our solar system. We simply had never detected one before. 2 years later, in 2019, a second interstellar object was detected. Comet Borisov, a clearly natural object about 1 kilometer across, passed through the inner solar system on a hyperbolic trajectory. It looked very much like a comet from our own Oort cloud, suggesting that the same kinds of icy bodies exist in other star systems. These were small objects. But rogue planets are much larger, and they too wander the galaxy on trajectories that can bring them through or near existing solar systems. The question is how often this happens, and what the consequences might be. In 2015, a team of astronomers led by Eric Mamajek announced a remarkable discovery. They had determined that a small binary star system, now known as Schultz's star, had passed through the outer reaches of our solar system roughly 70,000 years ago. Schultz's star is a dim red dwarf with a brown dwarf companion, and it passed within roughly 52,000 astronomical units of the Sun. That is about 0.8 light-years. Well, within the outer Oort cloud, the vast shell of icy bodies that surrounds our solar system. 70,000 years ago, modern humans already existed. Our ancestors were living in Africa, Europe, and Asia. They were making tools, creating art, burying their dead. And while they went about their lives, a star was drifting through the outermost reaches of our solar system, its gravity gently tugging on the comets and ice fragments that reside there. The gravitational effects of this passage were likely minor. Schultz's star is small, and it passed through the most distant and diffuse part of the Oort cloud. But simulations suggest that it may have slightly perturbed the orbits of some Oort cloud objects, potentially sending a handful of them on new trajectories toward the inner solar system. Some of these perturbed comets may not arrive for millions of years, their orbits so elongated that the journey inward takes geological ages. If a star can pass this close to our solar system, a rogue planet certainly could too. And a rogue planet passing through the outer solar system would have similar effects, perturbing comets and icy bodies, potentially sending some of them on collision courses with the inner planets. There is a tantalizing connection here to one of the great mysteries of our own solar system, the Planet 9 hypothesis. In 2016, the astronomers Konstantin Batygin and Mike Brown at Caltech published a paper arguing that the unusual orbital clustering of several distant trans-Neptunian objects could be explained by the gravitational influence of an unseen planet. This hypothetical world, which they called Planet 9, would have a mass of roughly 5 to 10 times that of Earth, orbiting the Sun at a distance of 400 to 800 astronomical units, so far away that it would take 10 to 20,000 years to complete a single orbit, so far away that it would be incredibly faint, reflecting almost no sunlight, virtually invisible to even our best telescopes. Planet 9 has not been found. Despite years of searching, no telescope has detected it. But the gravitational evidence remains intriguing. The orbital patterns of distant Kuiper Belt objects are difficult to explain without some large, unseen body influencing them. And here is where rogue planets enter the picture. One of the proposed explanations for Planet 9, if it exists, is that it is not a planet that formed in our solar system at all. It could be a captured rogue planet, a world that was wandering through interstellar space, happened to pass close enough to our solar system, and was gravitationally captured into a distant, elongated orbit. Capturing a rogue planet is not easy. It requires very specific conditions: the right velocity, the right trajectory, the right gravitational interactions with existing planets. But it is not impossible. Computer simulations by the astronomer James Vesper and others have shown that rogue planets can be captured by star systems, particularly if they pass through during the early chaotic period of planetary formation when there are many large bodies to interact with. If Planet 9 is a captured rogue planet, it would be one of the most extraordinary objects in our solar system. A world that formed around another star was ejected billions of years ago, traveled across the galaxy in solitude, and was then captured by our Sun. An immigrant world, a traveler that found a new home. This remains speculative. Planet 9 may not exist at all, or it may exist and turn out to be a perfectly ordinary ice giant that formed in our own solar system and was scattered outward. But the possibility that it is a captured rogue planet is real, and it connects the abstract science of rogue worlds to something concrete and close to home. Let us look forward now. Not thousands or millions, but billions of years into the future. In roughly 5 billion years, our Sun will begin to die. It will swell into a red giant, engulfing the inner planets. As it loses mass, its gravitational grip on the outer solar system will weaken. The orbits of the outer planets will expand, and in the chaotic interactions that follow, one or more planets or their moons could be ejected entirely. Europa with its subsurface ocean, Enceladus with its hydrothermal vents, Titan with its thick atmosphere. Any of these could become rogue worlds, carrying whatever biology they harbor out into the galaxy. And this process is not unique to our solar system. Around every star that dies, planets are scattered. Some fall inward and are consumed. others are flung outward into the dark. As the galaxy ages, the population of rogue planets will grow steadily, century after century, millennium after millennium. Let us extend this even further. Let us look at the very far future of the universe. The era of star formation will not last forever. The raw material for new stars is slowly being used up. We are living in the slow autumn of the stellar era. In roughly 100 trillion years, the last stars will burn out. The final generation will be the red dwarfs, those small, dim, miserly stars that burn their hydrogen so slowly that they can shine for trillions of years. But even they will eventually exhaust their fuel and fade. When the last red dwarf flickers and goes dark, the universe will enter what cosmologists call the degenerate era. A universe of stellar corpses, white dwarfs cooling slowly toward absolute zero, neutron stars spinning down, black holes slowly evaporating through Hawking radiation over timescales that make a trillion years look like an instant. And in this dark, cold, seemingly dead universe, rogue planets will still exist, trillions of them, drifting through the void, carrying their cargo of rock and ice and radioactive elements. Their internal heat will fade eventually. Radioactive decay is exponential, and over tens of trillions of years, even the longest-lived isotopes will be spent. The subsurface oceans will freeze. The last chemical reactions will slow and stop. But for a long time, for many billions of years after the last star has gone out, rogue planets with subsurface oceans will remain the warmest places in the universe. The last oases of liquid water. The last possible habitats for life. If any biology persists in those hidden oceans, it will be the last biology anywhere. The final thread of the living universe, stretched thin across an ocean of time and darkness, but not yet broken. There is something almost unbearably poignant about this image. The last living things in the universe, whatever they are, will not be creatures of light and warmth. They will be creatures of darkness and depth. Microorganisms, perhaps, clinging to the walls of hydrothermal vents at the bottom of a frozen ocean, on a planet that no star has ever warmed, in a universe where no stars remain, drawing their energy from the last atoms of uranium and thorium decaying in the rock below, reproducing slowly, evolving slowly, living slowly, but living. We have traveled a long way tonight, from the violent births of rogue planets, torn from their home systems by gravitational chaos, to the quiet depths of their hidden oceans. From the theoretical calculations of David Stevenson to the real, measured plumes of Enceladus. From the starless sky above a wandering world to the very far future, when rogue planets may be the last habitable places in the cosmos. And now, as we come to the end of this journey, I want to leave you with a thought about these worlds, about what they are and what they mean. We call them rogue planets. The word rogue suggests something wild, something dangerous, something that has broken the rules. And, in a sense, they have. They do not orbit stars. They do not obey the neat, orderly pattern that we learn about in school, where planets circle their suns in predictable ellipses and everything has its place. But rogue planets are not failures. They are not defective. They are not less than the planets that stayed behind. They are simply travelers. Worlds that took a different path. Worlds that were given a push, by gravity or by chance, and set out on a journey with no destination and no end. And they endure. That is the remarkable thing. They do not burn out. They do not collapse. They do not cease to exist because they left their star behind. They carry their warmth within them. Their heat comes not from outside, but from inside, from the slow decay of ancient elements, from the residual warmth of their own formation. They are self-sustaining in a way that even worlds like Earth are not. When our sun dies, Earth dies with it. But a rogue planet needs no sun. It carries its own fire deep within its core, a fire that will burn for billions of years after the last star has gone dark. Tonight, as you lie here and listen to these words, the galaxy is full of these travelers, billions of them, perhaps trillions. Right now, as your breathing slows and your thoughts begin to soften, rogue planets are drifting past stars they will never orbit, passing through solar systems they will never join, carrying their hidden oceans through the spaces between the stars, oceans that have never reflected a single ray of starlight, oceans that may be home to life that has never known what a sun is. Some of these worlds are older than our solar system. They were ejected from star systems that formed and died billions of years before the sun was born. They have been traveling longer than Earth has existed, and they will continue traveling long after Earth is gone. There is a lesson in this if you want to find one, a lesson about endurance, about persistence, about carrying your own warmth through the cold and the dark, about not needing anyone else's light to keep going. These worlds do not need a star to validate their existence. They do not need to be seen, to be real. They exist on their own terms, self-contained, self-warmed, self-sufficient, moving through the universe at their own pace, on their own path, answering to no gravity but the faint, collective pull of the galaxy itself. And they are not alone in their solitude. There are so many of them that, statistically, 2 rogue planets must sometimes pass within a few light years of each other. 2 dark worlds, each invisible to the other, drifting past each other in the night. Neither one aware of the other's existence. Ships passing in the night, on a scale that dwarfs anything we can imagine. The universe is a vast and mostly empty place. Between the stars there is almost nothing, a few atoms of hydrogen per cubic centimeter. The faint glow of the cosmic microwave background, the afterglow of the Big Bang, now cooled to just 2.7 degrees above absolute zero. And darkness. An ocean of darkness so deep and so wide that light itself takes billions of years to cross it. But it is not truly empty. The rogue planets are there, moving through the dark, carrying their heat, carrying, perhaps, their life, and they will be there long after the stars have gone, long after the last galaxy has scattered its stars into the void, long after everything that shines has stopped shining. In the very end, in the deep future that lies beyond all imagination, the rogue planets will be among the last complex objects in the universe, the last places where atoms are organized into something more than random gas, the last places where geology happens, where chemistry happens, where the laws of physics express themselves in something more interesting than the slow expansion of empty space. They are the universe's quiet survivors, its patient wanderers, its keepers of warmth in the long night that is coming. And so, as your eyes grow heavy and the world around you fades, take comfort in this. You are not so different from a rogue planet. You carry your own warmth. You generate your own heat, roughly 100 watts of it, radiating gently into the air around you. You are a self-sustaining system, warm and alive, drifting through the darkness of a sleeping world. And like a rogue planet, you do not need the light to be alive. You do not need the sun to keep your heart beating. Right now, in this darkness, you are complete. You are warm. You are exactly where you need to be. Out there, beyond the walls of your room, beyond the atmosphere, beyond the orbit of Neptune and the edge of the Oort cloud, the rogue planets are traveling. They have been traveling since before you were born. They will be traveling long after you are gone. And they do not hurry. They do not worry. They simply move slowly and steadily through the dark, carrying their oceans, carrying their warmth, carrying, perhaps, their quiet, hidden life. The galaxy is full of wanderers tonight, and you, in your own small way, are one of them. A warm body in a dark room, a mind drifting gently toward sleep, a traveler resting between journeys. So rest now. Let the stars keep their vigil. Let the rogue planets continue their long, silent journeys. Let the universe turn slowly and patiently, as it always has and always will. You are warm. You are safe. And in the morning the light will return. But tonight, the darkness is not empty. It is full of worlds. Good night from the Science Pillow.